Welcome to chapter 4. So in chapter 4, we're going to be looking at probabilities. So in statistics, we deal a lot with probability. So we're going to start off with some, definitions of terminology. One of the first terminologies we're going to deal with is an experiment. So an experiment in statistical parlance is essentially some activity with well-defined outcomes. So that is an experiment. So an experiment could include things like tossing a coin. For instance, when you toss a coin, you have two possible outcomes. You could have heads or tails. So this is essentially because you have well-defined outcomes. So this qualifies as an experiment. When you talk about an experiment, you have another related concept, which is the sample space. So the sample space would be the number of outcomes, the possible number of outcomes that you could have. So rather the outcomes that you could have. So that sample space is that set, is this set over here, which is H and T, So and in this case, the size of the sample space is 2. So that gives you the size of the sample space. Then a sample point is any member of this set. So in this case, we H or T are sample points, right? Then there's situations in which you have certain types of experiments where you have where you have to deal with permutations and combinations. So there are certain types of experiments where you have to deal with permutations and combinations. Just looking down. So in these kinds of experiments, you trying to you basically have to define the sample space using these kinds of counting rules. So a permutation is simply a situation where you are selecting n elements from so you're basically going to select n elements from a larger set of n elements, and when you're doing a permutation, order matters. When you're doing a permutation, order matters. Then with a combination, you are selecting n elements from a larger set of n elements, n uppercase, and in this case order doesn't matter. So when you're doing a permutation, you have, for instance, if you have this set, if you have the set A, B, C, if this is the superset, right? If you have this superset A, B, C, D, E, then for permutation, the set of permutations, so this is our set, the set of elements E is that. So then for permutations, the sample space, or the set of permutations rather, is going to include things like So you'll have this first possible outcome, which is so for instance, if you're looking for permutations of n is equal to 2, you'll have A, B, and you'll also have B, B, A. So and then you'll also have CD, C, D, and you'll have D, and so on and so forth. So essentially here, if you flip the order, it's essentially a different outcome. It is a different experimental outcome, and therefore it actually it expands the sample set. But if you had combinations, if you go to combinations, this is actually not the case. So for a combination, E, you'd have, so A, so you have, for instance, that's one combination, but you cannot have, this as a different combination. You cannot have this as a different combination. So you could think of, problems which include permutations. Could be things like password combinations. So interestingly, you could call these combinations, but these are actually permutations. Yeah. So technically, so a password is a permutation, right? Sometimes we call them combinations, passwords and key phrases, but actually permutations, because the order of text is actually going to matter in a password. Yeah. Then of course you can also have combinations. And situations which involve combinations, for instance, if you're doing a team selection, it doesn't really matter if you call team selection. So the order in which you select players does not change the team. So if I say Allen Iverson, then I say Mike Jordan, or then I say Mike Jordan, then Allen Iverson, it's really still the same two people that I've selected for my team. So you could have multi-step experiments. In this situation, you have more than one step. Yeah. So you can think of maybe tossing a coin several times. By the way, that would be a permutation, right? If you are tossing a coin multiple times, because you could have, for instance, in the first experiment, you could have something like head. Let's say you're tossing twice. Then the next you have tails. Then in another outcome could be tails. Then it could be tails, heads, and it could also be head. Yeah. So these are actually different outcomes. These are technically different outcomes because this is what you get in the first. So this is really a permutation. If you're going to look at try and generate the sample set, you wouldn't say that HT and TH are the same, because the interpretation is that this is what you get in the first trial and this is what you get in the second trial. So if you have certain an experiment, we call those multi-step experiments. Here's one example, for instance. Typically, you could use a tree diagram to visualize the outcomes. So in this case, we have the coin example. So you can see in the coin example, as already said, HT and TH are actually different outcomes. So you can actually generate this sample set using permutations. And this is what you refer to as a tree diagram. So a tree diagram is something that is going to help you visualize the outcomes in a multi-step experiment This is another example where you have completion times for a project. So in this project, you have two stages. In the first stage, you have design. The second stage is construction. And these are the durations which have been observed historically in execution of similar projects. So you can figure out from this that the completion time for phase 1 is either 2 or 3 or 4, and the completion time for stage 2 is either 6 or 7 or 8, because these are the only values which actually occur. And then from these you can actually construct. If you wanted to figure out the sample space, you can actually construct the sample space, and then you can construct the sample space, and then this can help you figure out the different outcomes, the possible outcomes. So in this case, you are coding by the number of months that each phase takes. So we have the 2.6, 2.7, and 2.8, and then you can see the total duration. So if I asked you what's the likelihood that project is going to take more than 10 months, you can actually figure it out from from historical data in this case. So if you're actually using historical data, then would refer to this technique as a relative frequency approach. You're actually using a relative frequency to figure out how long or you could also refer to it as an empirical approach, as you have some data from which you want to infer the future. So let's go back to this thing called combinations. So combinations, the formula is so a combination, let me insert a new equation. So essentially, a combination is if you have some combination C uppercase super N sub N. So it is essentially I need one of these. So it is essentially written like that, yeah. So it is so a combination is going to be, we need an equation here. So it is essentially uppercase N factorial, then lowercase n factorial into n minus n factorial. So that's a combination. So this could be useful to find out, for instance, the number of elements, the sample size. Could be very useful to to figure out the sample size if you are selecting, if you are selecting a certain number of outcomes from something with a sample size of n, selecting a certain number of outcomes from something the sample size of rather with a population of n. So for instance, if I wanted to know the number of teams, say I want to know how many different basketball team selections possible if I had 7 players. So that would basically be 7 factorial. 7 factorial of basketball team is actually made up of 5 players, so you have 5 factorial, then 7 minus 2 factorial. 7 minus 2 factorial is 2 factorial. So 7 factorial or 7 minus 5 factorial. So 7 factorial divided by 7 by 5 factorial is I hope people know what factorials are. So a factorial, let's say you have 7. Let me just do it with a 3 factorial. So let's say you have a 3 factorial. This is actually 3 by 2 by 1. So you keep on decrementing by one number, by 1 rather. So let's just go back to so 7 factorial divided by 5 factorial is actually going to give you 7 by 6. 2 factorial is still 2. Yeah, so this is 7 by 6. And if you divide by the remaining 2, then you're going to end up with 7 by 3. 7 by 3. You can actually get 21 teams. Yeah, 21 unique team selections from can get 21 unique selections from, if you have 7 players and you want to pick 5, you can actually get 21 unique teams according to this. Yeah. Permutations on the other hand, permutation so let me just insert a new equation. So permutations are given by this formula, which is essentially the factorial multiplied by the lowercase n. Yeah. Sorry, so it's given by this, which basically is going to work out to this equation. It's going to be n factorial over n minus n factorial. So if you're trying to figure out how many permutations you're going to have from how many different ways you can select. For instance, if now you have an alphabet, so you have an alphabet of 26 letters, yeah, and you need a password of 5. That's going to be too big. Well, it doesn't matter. Let's see. You need a password of let's say 20 letters. I hope that is small enough. Yeah, I want us to deal with a very big number. So the bigger the selection, the less the permutation based on this. So you have so you need a password of 25 letters. So 26 minus 25 is 1 factorial, which is still 1. So 1 factorial is actually still 1. So that leaves you 26 factorial possible. 26 factorial possible permutations. If you reduce the n, for instance, if you have 24 here, the result is going to be to so the result is actually going to have a bigger denominator, right? Because 26 minus 24 factorial is now 2 factorial. So if you have a smaller n, if the n is bigger, if you have a bigger n, then you have a bigger smaller n rather. You're gonna end up with a smaller. You're going to end up with a smaller denominator, and then you're going to have more permutations. But if you have a smaller n, because here we had the 25, but if you have a smaller n like 24, yeah, it means you're going to have a bigger denominator. Then you're going to have less. You're going to have a smaller number of permutations. This sort of makes sense. For instance, if you're choosing a password of 5 characters, yeah, if you're choosing a password of 5 characters, then you're going to have 26 minus 5, which is 21 factorial. So you're going to have less, because 26 factorial over 21 factorial is actually 26 by 25 by 24 by 23 by 22. Yeah, so that's actually a smaller number of permutations. So which makes sense, because the longer your password, the more possible combinations you have, and the more secure it is. The more secure it is. So maybe that's one thing for you to note in security. Then let's come to assigning probabilities. So you can have the classical method. So here with the classical method, all outcomes are equal. So if you're doing some kind of theoretical probability, like when you did the heads or tails, for instance, it is typical to use for this kind of work to assume that all the outcomes are equal. So if you're using an unbiased coin, then H of H and H is just as likely as H and T. And experimentally, if you do this, if you do a large number of trials, like 100, this is what is actually going to happen. Then of course you could have the what we call a relative frequency approach, which is based on, which is data driven. So essentially you have some data, then you infer the probability from that data. For instance, you have the number of months that it takes to complete a project. So if you're doing this kind of calculation, typically you actually use what you have observed. Yeah. So for instance, here we have the duration for the phases of project. So phase 1 is design, phase 2 is construction. So that means this is what you've observed, and you want to know what is the probability the project will take 8 months. So you've observed this once in 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be 1/9, a ninth of the time. That's what you observed, and that's the probability that you're going to assign. So that's the relative frequency approach. But sometimes you don't have the benefit of data. Yeah. So if you don't have the benefit of data, it means that you have to rely on some subjective. You make some educated guesses. This also happens. And you can refine this. You can refine this iteratively, but you have to respect the rules of probability, which is that you cannot have a probability less than 0, and you cannot have a probability greater than 1. And the sum of your probabilities, of your different probabilities, is going to be 1. So this brings us to the end of this first part of chapter 4.